In this video, we're going to discuss reductive amination. So as a quick recap, let's say that you're reacting an aldehyde or ketone with a primary or secondary amine. We're going to form an imine or an enamine. That's what we've seen. And the key thing here is we're doing so in the absence of a reducing agent. If I react with the primary amine, I form an imine. If I react with a secondary amine, I generate an enamine. But let's say that we do introduce a reducing agent like H2PDC or NaBH3CN. Instead of getting an imine or an enamine, the net result is an amine. Let's cross this out down here. We get an amine product with an A. There's going to be a reduction of the imine or enamine, and this process is known as reductive amination. So let's track the two processes by which we can do reductive amination. The first is by using H2PDC as your reducing agent. In this scenario, what we'd imagine is reacting with our amine, generating either your imine or your enamine, depending upon if you're reacting with a primary or a secondary amine to begin with. And then H2PDC would reduce the imine or enamine pi bond. That is to say, both the nitrogen and the carbon are going to receive a hydrogen in that reduction process. And if we're generating a chiral carbon, notice that we can form a pair of enantiomers or possibly diastereomers. Here, these are specifically enantiomers. So if H2PDC is present, we reduce the imine carbon-nitrogen pi bond, or if we had reacted with a secondary amine, we would reduce the carbon-carbon pi bond of the enamine, forming an amine. Then the other way you might see reductive amination written is with your amine, your trace acid, and this reducing agent NaBH3CN. That's called sodium cyanoborohydride. Now that's a selective hydride donor, and it's actually less reactive than NaBH4. What gives it its lower reactivity is this withdrawal from the CN group. It withdraws, making the hydrides have a smaller partial negative. And because it's less reactive than NaBH4, it actually cannot reduce the aldehyde or ketone starting material. Rather, NaBH3CN is going to have compatibility with the iminium ion intermediate. Remember, that's the last intermediate that is formed in the process of generating an imine or an enamine, where we've got the carbon-nitrogen double bond and the nitrogen has that positive formal charge. So it's safe to actually have NaBH3CN in that reaction mixture. It's not going to react and reduce the ketone. It only has compatibility with the iminium ion. So if we imagine the primary amine going through the mechanism, we'd attack, break the pi bond, do some proton transfers, eliminate water as a leaving group, and generate the iminium ion. It would be at this stage that NaBH3CN would become active, and we'd have a hydride addition. H- attacks that carbon, and we break the carbon-nitrogen pi bond of the iminium ion, and that would generate for us our amine. So both of these are valid ways to annotate and provide reagents for reductive amination. I would say the most common way is using NaBH3CN, but don't be surprised if you see H2PDC as well. And with the H2PDC method, don't be surprised if you see that as step 1, generate the imine/enamine, then step 2, reduce with H2PDC. So they could be written as separate steps, or you could see them included all at once. So that being said, let's do a couple examples of reductive amination. If I look at example 1, I'm reacting a ketone with the primary amine, trace acid, and I detect the NaBH3CN, so that means I'm going to reduce to make an amine as opposed to making my imine. What I'm going to do is make a bond from the former carbonyl carbon to my nitrogen atom of my amine. I'm then going to imagine that the amine still has its alkyl group. It would have one hydrogen, and I deliver a hydrogen to that carbon as well. And I would produce a pair of enantiomers. I generated a chiral carbon, I could produce that product, plus its enantiomer. Now, I predicted the product quickly and accurately there because of my little shortcut in reductive amination. What we need to make is your carbon-nitrogen bond, where that carbon is the former carbonyl carbon. We bond the former carbonyl carbon to your nitrogen atom. And then your nitrogen atom, of course, still has its alkyl group, but then it would have one fewer hydrogens. One fewer hydrogens, and then we also need to add a hydrogen to the former carbonyl carbon. That would be the net result. We make a carbon-nitrogen sigma bond. We add a hydrogen to the former carbonyl carbon, and the nitrogen will have one fewer hydrogens than it had to begin with. So why don't we do that for the next example as well, use that strategy. I'm going to take this primary amine, and I'm going to connect it to the former carbonyl carbon. this carbon here. That carbon will still have two methyl groups. I'll imagine adding a hydrogen to it, and the nitrogen will have one fewer hydrogens. Now, in this case, that's not a chiral carbon, so there's no stereochemistry there that's necessary. And you don't even really need to draw the hydrogen, but I find it can be nice to accentuate that in our mind's eye we are forming a carbon to hydrogen bond here. I'll maybe just draw that in gray. So that's our reductive amination product. In the next example, I see I'm reacting with a secondary amine, trace acid, and H2PDC, reductive amination. I'm going to make a sigma bond from the former carbonyl carbon to my nitrogen atom. The nitrogen has one fewer hydrogens than it had to begin with, and then I'm going to add a hydrogen to the carbonyl carbon. In this case, that is a chiral carbon, so I could generate this product, plus it's an enantiomer, where I'd then show that bond to the nitrogen on the dash perspective wedge. And looking at our last example here, I see an aldehyde, secondary amine, trace acid, NaBH3CN. I'm going to connect my nitrogen to what was my former carbonyl carbon. That carbon would, of course, still have its attachment to the benzene ring. And I'll add one extra hydrogen to that carbon. It had one hydrogen to begin with, and it will receive one hydrogen through the process of reductive amination. Now, I don't have to draw those hydrogens out explicitly, but they would be there. And in this case, no chiral carbons were generated. So let's go over that process one more time for the net outcome of reductive amination. We're going to imagine bonding the former carbonyl carbon to the nitrogen atom of your amine. You're going to bond a hydrogen to the carbon, which is being added in the reductive process. And then the nitrogen will have one fewer hydrogens. I'm going to repeat that process one more time for the very first example, just to accentuate that process once more. I'm going to imagine bonding my nitrogen atom to the former carbonyl carbon. The nitrogen atom will still have its alkyl group attachment, and the nitrogen will have one fewer hydrogens. So it had two to begin with, now it has one. And then I'm going to imagine a hydrogen being added to the former carbonyl carbon. Then I check for chirality. It looks like where I bonded the nitrogen, that is a chiral carbon, so therefore I would need perspective. I could draw this product, and it's an enantiomer. All right, so reductive amination is a very powerful way to generate an amine product by reducing the imine and or enamine that we would generate. And H2PDC specifically generates the imine carbon-nitrogen pi bond or the enamine carbon-carbon pi bond. And if we are instead to use NaBH3CN, sodium cyanoborohydride, mechanistically, that specifically reduces the iminium ion intermediate, which is a common intermediate in the pathway of forming both an imine and an enamine. NaBH3CN is less reactive than NaBH4 and does not have compatibility with the starting aldehyde or ketone, but it does react with the more reactive iminium ion intermediate, reducing that to generate an amine.